Um, we're going to have this session on the topic of recycling of wind turbine blades, and always ending up with this topic at the end of a conference day. I think we should all work for that. This very important topic also appears at the beginning of conference agendas. I hope you do agree. But let's start with Liu Yang, who's going to tell us on the state of the art within recycling of turbine blades. So I stop sharing, and Liu, if you can start to share your screen, that would be perfect.
All right, thank you. Well, good afternoon, everyone. My name is Liu Yang. I'm a senior lecturer at the University of Strathclyde. First of all, thank you very much for the opportunity to give this talk. I'm also the coordinator for the university strategic theme in sustainable manufacturing and materials. So today I'm going to talk to you about some of the existing technologies for recycling composites in general. And then I will also talk some of the work that we have done in this area, and particularly associated with wind turbine blade recycling. So let me start off by first just mentioning some of the programs that we've been working on. They're funded mostly by the UK Research Council. Our research in this area began back in 2011, and our effort mostly focusing on dealing with GRP, composites waste, glass fiber reinforced polymer composites. Our goal is to develop a upcycling process for recycling and reuse GRP waste. We have developed our technology now to the mid-TRL, and our next step is to looking for the opportunity upscaling to pre-commercial level, and that activity now is supported by the Composite UK, which is the UK largest trade association for composite supply chain. And of course, the composites in general are used in many different sectors apart from the wind industry. And therefore, the composite waste is a cross-sector issue. It is not wind industry specific. However, I do think the wind industry can play a significant role in driving towards a solution. Part of the reason is because you get this kind of headline in the press these days when the retired wind turbine blades are sent to landfill. Even though the same thing happening to a lot of more composite waste from other sectors. In fact, today in Europe, annual blade waste stream accounts for about 10% of total composite waste in Europe. That being said, the rapid blade waste stream has been projected. We're expecting, if nothing changed, 40-fold increase globally for the wind turbine blade waste over the next 3 decades. So I think soon this will become more than an image problem for wind sector, and it is worth thinking about a solution now and to deal with this problem coming up. The good news though is most of wind turbine structure in fact is recyclable and have done so accordingly. It is those wind turbine blades that are particularly problematic when it comes to recycling. And this image sort of gave a clue to why that is the case. Now, most modern wind turbine blades are made of glass fiber reinforced resins, such as epoxy, which is difficult to recycle on its own. Besides these composite materials, if you look at this, fractured wind turbine blades, there are other materials such as bow spoots, and sometimes that could be PVC foam, fillers, adhesives, and coatings, and paints. So it is quite a mixture of different materials in the system, to say the least. So developing a really cost-effective process to handle this kind of a heterogeneous material system is quite a challenge indeed. Nevertheless, over the past 20, 30 years, a number of techniques have been developed, and they're largely grouped into three categories based on mechanical, thermal, or thermochemical processes. And each of this process can also have different subroutines or variants, depending on the types of materials to be dealt with, energy consumption, throughput capacity, and costs, etc., etc. Um, there doesn't seem to be a silver bullet for all the composite waste in all areas and regions. So the different solutions and technologies will probably end up coexisting in the foreseeable future, which is a good thing from innovation point of view, I think. So in the next few slides, I'm just going to briefly go through some of the mostly perhaps researched techniques. First is the mechanical recycling. So in this technique, composites get crushed by the mechanical machineries and downsized from original size to anywhere between a few centimeter to a few millimeter. And these small downsized pieces can then be further screened or subsequently used either as a filler or fiber reinforcement. Um, the advantages of this technique is the simplicity. It's quite simple to set up, and it's been reported to require very low energy to operate. Um, the key issue, however, is that when it comes to the recyclates produced by this recycling technique, if it's used as a filler replacement, it has a very low value in the market and competing with some already quite cheap material. So economically, it's quite challenging to make it viable in the long run. If the fibers are used, they are normally not clean, so which cause problem in bonding with the resin if it's used in polymer system. When it comes to wind turbine blade, they're built with a very high durability even after it's being retired. So we have seen instances where the machine actually got severely worn or even damaged when trying to grind or shredding these blade materials. Now, currently, these type of operation mostly found in-house for recycling in-house waste. There are, however, some service providers in the US, in Europe. Um, Lastly, this process is still, I think, required for some other more sophisticated recycling processes, which I'm going to talk about next. So next is cement co-processing. In this process, the GRP or glass fiber composite blades or other waste materials crushed and then mixed with other waste components and then used as a solid fuel for the cement kiln production. This is using the organic fraction like in the system, a GRP system to replace the conventional fuel like coal in for cement production. And the glass contact in this instance will be integrated into the cement raw material due to similar chemical makeup compared to the cement raw materials. Um, some of you may know this technology has been developed and also have been industrialized in Germany. And this technology is being proven to reduce the environmental impact, as you can see from this chart here. Depends on how much of the waste that you are using in that composition, and is currently being promoted by European Composites Industry Association. And the other process is the Solvolysis process. This is a technique where which can is able to separate the polymer and fibers, and essentially it's using various different solvents to break down the polymer matrix and free up the fibers embedded in it. And this process can happen take place at an elevated temperature or pressure. Although some of the process, if you use catalyst or depends on the solvents, it can take place also at an atmosphere pressure. The advantage for this process is it requires relatively low temperature compared to process like using thermal heat. It has a wider range of solvents available for dealing with various different type of materials. So both the organic solvent, the inorganic solvent has been explored in the literature. As I said, its process are able to recover both fibers and a resin chemical components, which can be a very valuable material for using as a chemical feedstock or fuel. Um, the fibers recycled from this process are typically clean with a good performance retention, which is good also for reused fibers. I think the key issue for this process is trying to be developed more cost effective for GRP, particularly if we're talking about wind turbine blade at the moment, because the GRP or glass fiber composites are typically very much cheaper than carbon fiber composites. So currently, there's a technology providers exist in US, Japan, and Europe, including Sweden. I'm sure this topic will be discussed much more by the following speakers. So last but not least, there's a pyrolysis or fluidized bed and fluidized bed process. These processes are probably one of the most researched process in this area, both using heat as a way of breaking down polymer matrix, unlike in the Solvolysis process using solvent. So in this process is using heat. And pyrolysis typically carry out in the absence of oxygen to thermally decompose polymer into low molecular weight chemical compounds, which then could be used as a fuel or chemical feedstock. Whereas a fluidized bed process normally takes place in a hot air agitated sand bed and have very good mass and heat transfer. But it does burn off polymers through thermal combustion process. The advantage of these processes are widely practiced in other areas already. I think the biomass, the conversion using the pyrolysis product is a very good example. And these processes are relatively easy to scale up. And some of the processes like fluidized bed are naturally designed for running as a continuous process, therefore with a very high throughput capacity intrinsically. And these processes also, because of using heat, it's got high tolerance to contaminate materials and so and the waste mixture. So it's quite good for dealing with the end of life wastes. Both process has been reported to recover clean fibers. The key issue, however, here is, of course, using the high temperature, and then depends on what polymer system in the composites. It can be anywhere between 450 degrees to 600 degrees Celsius. So there can be some resin chemicals recovery if we talking about pyrolysis process, but there could be also no resin chemicals or any sort of material recovery in that regard from fluidized bed process. So you get just the fiber reclamation. When it comes to fiber, the process proved to be quite aggressive and can cause damage to these fibers. This is a particularly a problem for glass fiber. It suffer a huge strength loss when it's recycled through the thermal process. As you can see here in this graph here, the strength loss also depends on the temperature used in that process. Currently, there are, however, industrial operations available in the UK and Europe and the US. And in the UK, noticeably, company like ELG Carbon Fiber has been, really paving the way and pioneering the technology and also developing applications in this area. But they're at the moment particularly focusing on carbon fiber, again, due to the economical reasons. So let's just move on to talking about some of the work that we have done in this area. So at Strathclyde, we have developed a in-house fluidized bed process for fiber recovery, as well as additional fiber treatment to regenerate fiber performance. We have done a case study with a wind turbine blade where we have a 20 kilogram wind turbine sized and then feed into the fluidized bed process to recover the glass fiber in this case. As you can see, In fact, these fibers are already being treated using our developed treatment. And these treatment are just basically doing two things here. One is to regenerate the fiber strength, as you can see here. If there's no treatment, the fiber have compared to the normally would be on this level, the virgin glass fiber lose a lot of strength. But if we apply the treatment, we can recover a lot of these lost strength. And the other function for this treatment is to produce a good bonding towards the polymer. In this case, we have tested with a polypropylene thermoplastic system and also epoxy. And both we can see that without any treatment, you get, again, some of the poor bonding here, but if we actually regenerate this bonding, we can make this work. Now, these fibers can be subsequently reprocessed. In this case, we're using essentially a paper making process as a wet dispersion process to make this type of fiber mat. And these fiber mats can then be further used to manufacture either thermoplastic composites using compression molding here, or thermoset composites using vacuum infusion process. Um, so we the testing on the composites property as well, using these recycled fiber or recycled and regenerated fibers. The results are here. So as an example, the glass fiber composite strength. On the very left-hand side, you have a polypropylene alone, and next to it is the composites with a virgin glass fiber. And if we just use the recycled fiber without any treatment, we can see we lose about over 40% of performance. However, if we regenerate the strength of the fiber, we recover almost half of these lost performance. Now, if we also fix the bonding problem, we can make the actual composites using recycled materials almost in the same performance as the new composites materials. With this outcome, we decided to make using these technology to make something using with a small wind turbine blade. So we have got a small 3 kilowatts wind turbine blade as a control or as a baseline commercial blade available, and then we use the vacuum infusion process, and with the recycled and regenerated fibers from the retired wind blades, and molded using the vacuum infusion process to make the prototype. We have done some initial bending tests that showed that our recycled blade is you've got enough stiffness compared to the commercial blade, and also that both of the blades have similar weight. So just finish off by concluding some of the points I touched on. I think composite waste is expected to continue growing, and the wind sector has opportunity to make some significant contribution. There are various recycling technologies being developed to different degree, and I think the diversity of these different solutions is really good for meeting different requirements. There needs to be more support in R&D in order to develop all various different technology to the commercial viable level. And I just want to finish off maybe the last point saying, apart from recycling, it is also important really to focus on waste prevention and reduction, and also more developing more recyclable materials. With that, I thank you very much for your attention, and I'll be happy to answer any of your questions.
Thank you, Liu, for this overview. There's one question that has come in so far towards the beginning of your presentation. What is the definition of recycling? If you, for example, mix granulates and reuse it in other application, doesn't that produce an even more difficult waste when that material has reached end of life? Have you got thoughts about this?
If I understand the meaning of the question, you're talking about sort of how the first round of recycling, or how from the initial material they have impact to further down the applications based on the recycled material. I think most efforts so far from what I've seen is mostly focused on just developing some viable process to cost effectively recycle materials. The the impacts on the sort of multiples recycling capability has not been really, I think, studied at this point. I do think that if the question has a valid point, though, is that just because you're seemingly doing something, trying to take back some of the waste material, the care should be really, attention should be paid towards whether that process is actually the environmentally make sense. I don't know if that's my thought on that. Yeah.
Well, thank you. For the moment, we haven't got any further questions, so I think we'll collect if there are further ones coming in and take them at the end of this session. Wonderful, thank you. So we've been looking in the project of Reko Wind and Recomp into what is actually circular economy in the management of end-of-life of wind turbine blades with a Swedish perspective. And I will guide you through some overall numbers. We will look at what's done today, and that is already touched very much by Louis' presentation. So we will not spend that much time on that, and also on the value streams from recycled materials. But also look at what are the motivations and where are we going in influencing tomorrow's end of life. So some short numbers, and I think we're all kind of ambassadors of the wind energy, and that means it's valuable to bring things into context. And I'd like to point out that we should remind ourselves that the energy payback time of a wind turbine is definitely less than a year. On an 8 megawatt Siemens Gamesa offshore turbine, we can say it's less than 7.4 months, or less, about 7.4 months, and for an onshore low wind site with a Vestas 4.2 megawatt, we are ending up with 7.6 months for the energy payback. And of course, you're all aware of that. This is depending on where the site is, what the wind conditions are, the distance to the grid, etc., 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 and how much you actually look at in your wind farm. And the figures that I named, that is only the actual wind turbines, excluding the foundations and any other infrastructure. Whilst we're looking at the lifetime of 20 years or more. And as Leo also pointed out, the good news is that up to 90% of the wind turbine, as it's known today, is recyclable, because many parts are homogeneous metal parts that have that can be fed into existing recycling processes. So it's really the polymers that are giving us troubles here. And looking at the mass, we're looking at some percentage of a total wind turbine that really causes this difficulty. Nonetheless, we will have to take care of it. In order to estimate the amount of material that has to be taken care of at the end of life, there are a variety of estimations out there. In literature, you can find anything between 8 and up till 13 tons per megawatt rated power of fiber reinforced polymer composite. Wind Europe has been even more conservative and has stated it's a 12 to 15 tons per megawatt rated power, possibly because they've also included the nacelle housing in their estimations. In our report, we went back to sort of an average on 10 tons per megawatt rated power, which seems to be consistent over time. So we've been looking at the installed fleet in Sweden and make some derivations on when they will be taken out of operation, and have thus made an estimation per year and a more general estimation of the 5-year period. And we're now in a between 2020 and 2024. We should start looking at solutions because we've got a volume of 740 tons a year, but that is quickly going up, almost 5-doubling to 3,500 up until 2029, and then continuously increasing, and it's almost 3 times as much when we're looking at the years before 2040. And of course, I think what we know now, we can all expect that this increasing trend will continue as we are employing more and more wind turbine in our energy systems in order to be renewable and in order to transition towards a fossil-free economy in total. There is some, and I think, Leo, you've touched upon this as well. Wind turbine industry is not the only industry in Europe supplying, so to speak, or having the problem of this difficult to recycle material. It is estimated that by 2025, it's only 10% of the total estimated thermostat composite waste in Europe that is coming from the wind industry. But it not only seems to be, I think it really is a driver that this industry is so much connected with the picture of this 3-bladed wind turbines that is a symbol for the industry, of course, and making up big landmarks. So that is the big awareness in public, and as you've shown headlines before from the press, this is increasing pressure for the wind industry to take care of this problem, much more than other industries that are not in first place connected, visibly connected with this question. So let's see. Well, the buzzword of circular economy, what does it actually mean within the topic of wind turbine blades? What is circular action within this field? And you're all very aware of things that the industry is doing because of many reasons, but it is also the very first circular action that you can do with your assets. You take care of it, you maintain, and you repair, and you probably also do actions in order to extend the lifetime from what was originally planned. The next step within circular economy is if I'm not able to use an asset any longer, I transfer it to someone else who wants to use it. So turbines are going very much to a second-hand market, much incentivized through the different countries' subsidy schemes. So what we could note in the Swedish market is that there were quite some turbines transferred to Ireland in the past, but we've also seen small single turbines entering Sweden as a second-hand market, rather from the Netherlands. And in a circular economy, if nobody wants to use the parts as the original function was meant, then you trying to reuse the asset in a different way. And for wind turbine blades, you've all seen those nice pictures of garden furniture or this popular playground in Denmark. And I've just heard the other day that playground really was maintenance free, really. That was made out of wind turbine blades. And what you look at here is pictures of different concepts for bridges. So, I mean, a structure as a wind turbine blade designed and manufactured for a long durability, for being able to handle both dynamic and extreme loads, is of course of you or should of course be usable in other infrastructure parts or in buildings where the strength of this part actually still could be used. Another part that is often covered within a circular economy, and one could argue how circular that is called energy recovery, and in principle that is just incineration, which is problematic because the glass fibers in glass fiber reinforced polymer composite is not cannot be combusted, so it results really in large ash residues when incinerated, and this is another picture of those horrible headlines that one could see at an island outside Norway that is simply completely used for landfilling of incineration ashes. We don't want to see much of this. Leo has already guided you through what's out there in terms of recycling actions, and maybe I can just add a few viewpoints from a more global perspective. You said that available on the market and preferred by the wind industry right now, that is the co-processing and cement kiln. And probably there's one reason for it is that the cement industry really is used to granulate hard material, because as you said, that is really a challenge. When we were talking to the waste and recycling companies, they're really not fond of taking in glass fiber reinforced plastics or polymers into their processes, because it's just so difficult for them. I mean, if you look at it, the advantage is that about 75% of the material that's used in the cement industry can be substituted. But I agree with the question of one of you guys that are listening today, that you got to think about the next step as well. But for the moment, that is the most popular solution. What we all see here, of course, independently from these processes that have a higher TRL level that are upscaled and available, and also the technologies that are still at a lower TRL level, is from a circular economy perspective, is really what I pointed out when talking about the reuse. You're not only taking care of material, you are destroying a design and a strength in the construction. So recycling really is, from a circular economy perspective, really the last door to go instead of going to landfill, because one is really destroying more values than just on a material level. But let's look at where recycled value streams actually could find a second life. There is an increased demand for recycled polymers in the packaging industry. So as we're all trying to make our processes more sustainable, there's a bigger demand for a recycled polymer fraction. That is the first one. Then when it comes to glass fibers, we've seen corporations starting from, for example, wind turbine blade manufacturers, with in kind of a symbiosis process with manufacturers of either glass fiber insulation material or even glass bottle manufacturing. There are some intermediate steps needed in order to make that work, but especially from a production perspective, it's also interesting because, and we haven't touched upon that, during manufacturing of wind turbine blades, there is a 30% production waste also occurring. So that makes it necessary to really get cooperations going. One could also imagine that the advancement in 3D printing for low strength application could be a very good partner for such cooperation. Generally, we're very much aware of that when we talk about glass fiber reinforced polymers right now in the wind industry, we'll see more carbon fibers in the blades to come. Not only the ones that are installed today, but the ones that have been installed for about 15 or 18 years ago. So we will be handling not only glass fiber but carbon fiber reinforced polymers, which is giving some incentives because the price of virgin carbon is much higher, and that could actually bring things towards a more economic way for different recycling options. But we should also look at that the automotive industry is already forced by regulations to take a bigger responsibility. So there needs to be cooperation between industries that have the same kind of problem. And what we can see, there are some first drafts on the table, for example, in France, that also the wind industry will be regulated in some years with a producer's responsibility. which means that they are due to take care of their products at the end of life. We'll see how that develops. And then one interesting stream that could be coming up is that the recycled oil fraction is meeting a higher demand in refineries, so that they also can do what they can in order to be more sustainable and include more recycled share or within their refining process. I don't see any clock right now, Cecilia. I think you are soon there to continue. Just one more outlook. Recycling symbiosis processes. I have touched upon that. It's cement industry, chemical industry, and the glass industry that are quite close. But I think what we will see within the wind industry is also that there will be new business models coming up. Either in one way or another, I imagine that there's a possibility for blade return systems. If it's the manufacturers themselves, or if it's other market actors, that we'll see what turns out with that. But I think that is one of the ways the industry could go furthermore. We've touched upon the other points. One thing I would like to point out in a market like Sweden, where we don't have the manufacturers in the country, but we're one of the big markets in Europe still. And I think a more coordinated power of purchase that I deem so far to be untapped would be really favorable. That the owners and project companies really not only start to make their requirements when purchasing a turbine, but also evaluate on that topic and don't have it like the last thing on the list, but to really include that in their purchase decision. Time is running, so I take and finish this here. As I said in the beginning, this work has been mainly financed by RECO Wind, financed by the Swedish Energy Agency, and we are combining our efforts with another project which is called RECOM, financed by the innovation agency Vinnova. We've got partners on board that are supporting us in our actions, for example, Energiforsk. And this is setting the scene actually for my colleague Cecilia. Yeah.
Thank you, Tanja. Me and Tanja are working in the same projects, and I'm focused on the chemical recycling of end-of-life wind turbine blades. And I work with Solvolysis, as Leo touched on the first talk. This will be more focused on Solvolysis. And the outline for my talk is about, I will first focus a little about Blade Materials Challenge and talk about what Solvolysis is. And then I will present our results. And then I will give some conclusion and future work. So why is it so difficult to recycle thermoset composites? That's because a thermoset is composed of both a fiber and a cured thermoset. And this composite cannot be dissolved by common solvents, and you cannot remelt it like thermoplastics. The only thing you can do today is shred it and mill it with mechanical recycling, and then we get a fiber that's not so good for reuse, as Leo told us. And we also have another complexity, is that the wind turbine blades also are composed of a mixture of different materials, not only glass fibers and thermosets. As you can see on this picture, we have the blades that we have used in our study with Solvolysis. And to the left, you can see one blade. It's a big foam core with balsa wood. In the next picture, you have a white foam core. It's based on PET. And in the bottom, you have a green plastic, that's PVC foam core. And then you have the very complex end-of-life blade to the left bottom with many different plastics. So a chemical recycling process needs to be able to handle all these different polymers to work. And if you look at the overall picture of a blade, you have approximately 70% of inorganic glass fibers and fillers that go to ash if you combust it. And you have a 30% polymer load from balsa wood, thermoplastic, and thermosets. So our aim in our project were to develop a solvolysis method that can handle all the different materials found in the end-of-life blade. It should be much more easy to work with the production waste that Tanja touched on. But our work can be focused on the worst waste, and that is end-of-life wind turbine blades and other composites that are end-of-life. We work with chemical recycling and we utilize solvolysis and one solvent that works at high pressure and temperatures, water, could dissolve the thermoset composite. And we can retain two product streams, clean glass fiber, and then they have chemicals that end up in oil. And these two streams would like to reuse in secondary products. So the solvolysis oil, we believe, could be a feedstock for refineries, these existing refineries. And we can, in the future, probably produce plastic monomers, chemicals, and fuels from this oil, or other plastic oil that we can produce in the future. The recycled glass fibers could work as a replacement for virgin glass fibers in thermoplastic products and fillers, as Leo presented to us. So what is solvolysis? Solvolysis is a thermochemical process that works at high temperature pressure, and it's also called hydrothermal liquefaction, HTL. And we work between 200 and 400 degrees, and we have a high pressure between 5 to 250 bars. And this is slightly lower than the pyrolysis method. We utilize green solvents, water and alcohols. And at these temperatures, water gain unique properties. And we enter the area, as you can see to the diagram to the right, the subcritical region of water, that water can act as an organic solvent and diffuse into the composite and react with the bonds between fiber and thermoset by hydrolysis or radical reaction and release the fibers. And this method will give us cleaner fibers and higher strength fibers compared with pyrolysis and mechanical recycling. Our experiments we made in small scale. We use this vessels that you can see to the right, and we use 0.3 to 0.5 gram, and we heat it up and then we fill it with solvents you want to use and catalyst, and then we heat it up in the oven. It's a very small scale screening we have been working with. So now I will present our results. And on this slide, you can see the reaction times for the different materials from the wind turbine blades to the right. And after working 1.5 years, we have optimized our conditions, and we found two conditions that work quite well. We have water combined with the alcohol, and then the catalyst, potassium hydroxide, and we work at 330 degrees, 175 bar. And it's very essential to add an alcohol, otherwise we don't get any reaction at all. You can also work with only organic solvent, and it works very well with the ethylene glycol, 270 degrees and 175 bars. And if you look at the different glass fiber composites that you can find in the blade, we have compared the polyester-based blades with epoxy blades. And you can see it's a big difference between the reaction times. An epoxy blade takes approximately 16 hours in our reactors and give us 64 to 75% yield. Instead, the polyester is degraded faster, 4 hours, and it's degraded more than 90%. if you compare with the foam core react in our Solvolysis, and they also degrade very fast, and they are dissolved completely over 90% yield. So epoxy blade are the hardest to degrade. So now I will present some results also from the previous slide was on milled samples. We also would like to try out how it works with the pieces of blade, but should be less energy for milling all the samples. So here is the data from a 10-gram piece of a blade. And to work with pieces, that we need to do when we need to add even more reaction times. And we have first ethylene glycol in 16 hours, and then we have a water step for 4 hours. So in total, 20 hours in our reactors. And then we receive the product fractions to the right. You can see the piece of the blade, A, and B fraction is the glass fibers we get out, and C is the Solvolysis oil, and D, that's the wood pulp fraction that we get out from the piece, because in this small piece we had a foam core of balsa wood. So we got 3 product streams, and the yields are approximately 65% of glass fiber, 15% of the oil, and 13% of the wood fibers. So now I will present the quality of our fractions. And on this slide, you have the data so far we have on the recycled glass fibers from the Solvolysis from the epoxy blade, from the pieces. And you can see the SEM pictures, and this is on the best fibers that are clean. And you can see that these fibers are really clean. That's the pictures to the left. And you also have a reference picture on the glass fiber to the right. But if you look at the picture, we also have clusters of fibers still clogged together. So we still have a resin component in this glass fiber fraction. And if you measure the chemical composition, we realize that we have approximately 10% of organic residue from the thermoset left. So now over to the data from the Solvolysis, the preliminary data from the Solvolysis oil. And this is also from the epoxy blade piece. And if you look at the oil, it's mainly composed of polymers. And we have a small level of aromatics. And we can see that we have managed to remove the nitrogen from the epoxy resin and the chlorine from the PVC, if they are included in the samples. So that's really good, because you need to remove all the ions to reuse the oil as a drop-in fuel in the refineries. The chemical composition I have chosen to show in a Van Krevelen plot is quite complicated, but oils are usually presented like this when you use it, the fossil oils and all other oils that you develop. And when you're working to producing oils, it's very important to remove all oxygen content in any polymer. So the glass fiber composites are around 0.8 to 1 oxygen carbon on the x-axis on this plot. And if you do oil, then we move to the left, and then we have the Solvolysis oil on 0.2 oxygen carbon ratio. And this is really good. We almost remove all oxygen, but still, if we would like to use it to the fossil oil supplement, we need to take away the additional 0.2 and enter the zero area. So we need upgrading. So it's not the only process we need to do. We also need to work additional to get the right oil quality to replace the fossil oil with plastic oils. The good thing is if you do oil from wood, you get bio-oil, and this bio-oil is approximately the same composition, and we can probably use the same upgrading systems in the future. So chemical recycling is problematic. We have a low yield of the high valuable Solvolysis oil. At our small study, we had approximately 15%. And that's due because we have high fiber and fillers content. But we believe that this oil could be useful in the future after additional upgrading. The recycled glass fibers, they are more expensive than the virgin ones, and they also have lower quality still, and they are short and of random size. Another problem that not so often people talk about is that the wind turbine blades have the PVC content in the foam cores. And PVC complicate all chemical recycling and also the energy recovery by combustion, because PVC at high temperatures and pressures react, and when you get hydrochloric acid that corrode all equipment. So that means that also the recyclers working with energy recovery don't want to burn the wind turbine blades of this issue also. So to summarize, I would like to say that we need to create circular streams from glass fiber composites and wind turbine blades. We need to work on the technical solutions for the approaching legacy of end-of-life waste. We need to work on new solutions. We need to combine the mechanical and chemical recycling methods to reduce the reaction times, and also to remove some components to get a better chemical recycling method. We also need to work on reuse and remanufacturing of the good blades. So we only do chemical recycling on the blades that are destroyed. I also want to point out that we need to work on circular design of all new glass fiber composite products. We need to plan from beginning for a second life usage and the easy dismantling of, for instance, the blades. We need also to think about the mix of materials that we're using inside the blades and all other composite products. If you mix right, we can build up a sustainable recycling method. And lastly, I think we need to think about to exclude the PVC from all designs of glass fiber composite products and carbon fiber products. So that's also a little about material and chemical recycling. I will thank you for your attention. Tanja, the word is yours.
Thank you, Cecilia. Thank you for giving us this deep insight into the chemical process of solvolysis. Please keep your camera on. You can stop sharing, and I'd like Leo also to put your camera on if you can.